A little while ago, we learned about some things called a linear and quadratic approximation. We learned about those things and how we could approximate functions using those. And what I want to show, now that we're talking about Maclaurin and Taylor approximations, how we can get some interconnectedness between all of these things and scale up from a linear approximation all the way up to a Taylor or Maclaurin approximation. So let's first remind ourselves what we said in regards to a linear approximation. Let's talk about these guys first. A linear approximation. And a while ago, we said that a linear approximation would be this. The formula for it, for some x value near 0, we'd say that f of x is going to be approximately f of 0 plus f prime, so the derivative evaluated at 0 times x. And graphically, what's going on here is if we have a function, so if this is xy, if we have a function that maybe does something like this, okay, something like that, that our linear approximation would be constructing a tangent line at x is equal to 0 for this function. And it would look something like this. And then we would end up using this tangent line to approximate values of our function. So that is f of x. That is what a linear approximation is doing. But you can see, looking at this function in particular, I mean, once we get even just a little bit away from 0, it starts to fall apart a little bit. So we asked the question, okay, do we have any better approximation tools that we could use? And we saw that the answer was yes, that we have this other thing called a quadratic approximation that we could construct. A quadratic approximation. And its formula, we saw that to be for x values near 0, that f of x is going to be approximately f of 0 plus f prime evaluated at 0 times x, and then we add on f double prime. Let me make that a little neater. F double prime evaluated at 0 over 2, and then times x squared. And this first part here should look very familiar because it's just our linear approximation. And now we have this quadratic part that involves some second derivative information. And, maybe that makes sense and all, but we asked the question originally like, hey, why does this 2 show up? Why is that 2 there? And what we said was, okay, let's make sense of this. We said, okay, this is a quadratic approximation. So what if we construct a quadratic approximation for a quadratic function? So what we ended up doing was defining a function as a standard quadratic function. So we had g of x is equal to ax squared plus bx plus c. And we said, hey, we need to construct a quadratic approximation for this. And we expect, since this is a quadratic function, that our quadratic approximation and this should match. So what we ended up doing was, hey, we need to recover a, b, and c from here using some derivative information. So we evaluated this at 0, and we ended up finding that that is c. And then we can take the first derivative of this guy, and we find that to be 2ax plus b. And then we continued to evaluate this at 0. So first derivative evaluated at 0, we see that that's b. So we've already got our b and c out. And now taking the second derivative of g, we are going to get what? Second derivative is 2a. And then evaluating this second derivative at 0, we just get 2a out. But we don't want 2a. We want to have just a. And in order to get that, we need to divide both sides by 2. So we end up with g double prime evaluated at 0 over 2, and that is equal to a. So we've recovered a, b, and c now. And when we construct a quadratic approximation for g of x, for x values near 0, so if we were to just write this out real quick, for x near 0, g of x is going to be approximately, and we just fill in what we have here under our formula. So you can see that this is now c. We have g of 0 is c, plus g prime evaluated at 0 is b. So this is plus bx. And then we have plus our second derivative evaluated at 0 over 2 is equal to a. So this is plus ax squared. And you can see that this right here matches what we have over here. So that matched our intuition, and that helped us figure out, okay, that is really why this 2 is here. That gives us some nice intuition. Now, moving on from that, we ask this question to go from a linear to quadratic approximation, like, hey, can we do better than this? Because now this quadratic approximation gives us this nice parabola here to approximate our function. But the question that we can ask again is, can we do better than a quadratic approximation? And that is what allows us to arrive at what we've been talking about lately, mainly talking about Taylor and Maclaurin approximations. Taylor and Maclaurin approximations. Maclaurin approximations. Approximations. And what we've seen with those is this. And I want to give you some intuition. That's really what I'm after here. I want to use a similar argument to what we had for quadratic approximations of why this 2 made sense and apply that now to talk about why these Taylor and Maclaurin approximations are the way that they are. So first of all, let's just write out in summation notation what these guys are. So we'll first talk about a Maclaurin series and a Maclaurin approximation. We'll first talk about that. So we can say for x near 0 again, for x near 0, f of x is going to be approximately, and it's going to be this sum here, this sum. We can go from I is equal to 0 up to n, and it's going to be f and its ith derivative evaluated at 0 over I factorial, and then times x to the ith power. And this can look a little nasty just as summation notation under sigma notation, but don't worry, we'll break this down. And similarly, a Taylor approximation is just a more general form of the Maclaurin approximation. So rather than evaluating this at 0, we're going to have this. So let me put this in green. A Taylor approximation says for x near 0, f of x is going to be approximately, now this is sigma, so the sum from I is equal to 0 up to n still, but now we have f to the ith derivative, and now this is being evaluated at some a value, all right? And then this is over still I, make that neat, I factorial, and then we have x minus a to the ith power. This is a Taylor approximation, and you can see it's just a general form of what we have over here. If we let a be equal to 0, that's what we have exactly over here. Now that we have these two sigma notation things going on, I really just want to start to break this down and give you some intuition. That's what we're after. That's what we're moving towards. So in order to do that, I am going to play out a scenario. I'm going to let n be equal to 4, okay? And then we're going to write this out. We're going to write out this Maclaurin approximation and start to get a feel for what it's saying. So we can say for again x values near 0, that f of x is going to be approximately, and then we just play out what we have in here. So this is going to be f and the 0th derivative of that evaluated at 0 over 0 factorial, and then we have times x to the 0th power, and then we have plus. I'll just continue to fill this guy in here. It's evaluated at 0 over 1 prime, and then we have x to the first power, and then we have f, second derivative of f, evaluated at 0 over 2 factorial times x squared, and then we have plus f, and our third derivative of f, evaluated at 0 over 3 factorial, and then times x cubed, and then last one here. So we have our fourth derivative of f, evaluated at 0 over 4 factorial, and then times x to the 4th power. That's writing out this Maclaurin approximation when n is equal to 4. This is what we have here. And again, this is a better approximation than what we had in quadratic approximation and linear approximation land. And mainly, I'll get to that. I'll show you that they're both in here. But first, I want to use a similar argument to what we played out up here when we were trying to say, like, why does this 2 exist? I want to now play out a similar argument and say, why do all of these denominators exist? And we're going to do a very similar thing. So now I'm going to define a new function. So this is going to be h of x. And h of x is going to be this giant polynomial. So it's going to be, h of x is going to be ax to the fourth power, and then we have plus bx to the third power, plus cx squared, plus dx, and then plus e. And what we're going to do is similar to what we did up there. We're just going to start taking the derivative and evaluating it at 0 and see what we get. And we want to recover a, b, c, d, and e. That's our goal. So let's take some derivatives here. So we'll find the first derivative. That's going to be 4ax cubed plus 3bx squared plus 2cx plus d. Okay, and then second derivative. Let's keep going. 2ax squared plus 6bx plus 2c. And then we'll take the third derivative. All right, third derivative. This is going to be 24ax plus 6b. And then lastly, we're going to look at the fourth derivative. So the fourth derivative of h is going to be 24a. And now what we want to do is evaluate all of these at 0. So we find that h of 0 is going to be what? It's going to be e, okay? And then we have h prime of 0, and that's d. And then we have h double prime at 0 is going to be 2c. And then we have our third derivative of h evaluated at 0, that is 6b. And then we have our fourth derivative of h evaluated at 0 is 24a. And now, 24a. And now what we want to do is just recover. Remember, we just want a, b, c, d, and e. We already have d and e. And in order to get c, we're going to divide both sides by 2. So we have our second derivative evaluated at 0 over 2 is equal to c. And now, maybe this is starting to ring a bell, because this is exactly what we did to find the quadratic approximation. And that is, I just want to show you that, in this Maclaurin approximation, this right here, these first two terms is our linear approximation. Maybe I can write that out. Let me get that in pink. Pink, not green. Let's go pink. This is our, I actually don't want pink. Everything else is in pink. Here, I'm running out of colors. Here, this is our linear approximation. That's what I want to show you. These first two terms are our linear approximation. Our linear approximation. 2 P's. There we go. And then these first three terms here, these first three terms should also look familiar. And I can do this in purple now. The first three terms are our quadratic approximation. So both of the things that we originally started out with are baked into here, and now we are getting more, we're getting higher derivative information. So again, that is where that 2 comes in from. It's right there. Now, let's keep going. We're getting closer and closer. Now, in order to recover b, we need to divide both sides by 6. So we're going to have h, and then this is the third derivative evaluated at 0, and we're dividing that by 6 in order to get b back. And then lastly here, our fourth derivative evaluated at 0 over 24 gives us a back. So we have now a, b, c, d, and e. And here's the cool part. When we look at these factorials, what do all of these represent here? So 4 factorial, that's 4 times 3 times 2 times 1. So that's 12 times 2, that is 24. And that's exactly what we have down here. And same thing with 3 factorial. That's 3 times 2 times 1. That's 6. So you can see this pattern happening. 2 times 1 right here. That's 2 right here. So that's what we need to recover a, b, c, d, and e. That's why these denominators, these factorials in the denominators need to exist. And hopefully that can give you some intuition. And if you ever forget this, maybe you can come back to a derivation like this. And hopefully this can give you some intuition. But I think it's really cool how we could scale up from what we originally learned in linear approximations all the way up to these higher degree approximations that are represented in Taylor and Maclaurin approximations.